Good afternoon. My name is Jae-han, and today I'm going to talk about detecting low abundance pathogens using electrokinetic concentration processes. I'm from MIT Electrical Engineering and Biological Engineering. In any kinds of sensing, not just the biosensing, you always face a certain set of unique but universal challenges. And one of them is the fact that your target molecule that you are trying to detect is often present at very low concentration and very low abundance. Present a very unique problem. Regardless of last 2 decades, there has been a lot of advances in developing novel and innovative biosensors utilizing different physical mechanisms. But no matter how sensitive your sensor may be, the fundamental limitation that comes from the low abundance of the target is not easy to solve, simply because your target molecule may be present only a few copies in a given volume, and it takes a certain minimum amount of time for these molecules to have a chance to meet the sensor. So, even before your sensor detects the very first event, it may take a long time. That leads to a very noisy signal and all kinds of problems. So this has been a fundamental issue that has been limiting the progress of this area for so long time. And in certain areas of biosensing, this is actually not a problem, especially for detecting nucleotides, mainly because we have a very unique chemistry called PCR that actually takes the small number of target molecule and amplify them into a larger number. So we actually reproduce and multiply these targets, and then we don't have to suffer from this low abundance issue. And that is the reason why pretty much all the sensors that we are using these days are relying on this chemistry. But it still has some inherent issues. This amplification chemistry is oftentimes susceptible to various kinds of compounding factors, inhibitors, and sometimes it amplifies a noise signal, not the actual signal or target molecule you want to detect. So in my group, we have been thinking about alternative strategies. So right now, the entire biosensing field is really relying on this one chemistry called PCR, and it works, as you can see, in the current COVID-19 pandemic. But can there be any other alternative strategy? And we propose that this pre-concentration idea can be an alternative and even complement the current amplification strategy. Why? Because oftentimes we have a sufficient volume of the sample, raw sample. Let's say biomedical detection of biomarkers from urine or blood. It is reasonably possible to get a milliliter level samples. And even though the concentration of your target molecule may be very low, if you can somehow bring that molecule and concentrate it without losing them and bring them into a very small volume, like a picoliter or a nanoliter, we can achieve similar levels of signal enhancement without suffering all these issues that comes with the amplification chemistry. So my group has been working on this idea for almost 15 years now. And about 15 years ago, we came up with these ideas of microfluidic concentration devices, where we can take a fluid that contains a very small copies of target biomolecule, whether that is protein or DNA or virus or bacteria. We can bring them in and then we trap them while passing the liquid or water so that effectively you can concentrate them. So, we did publish many different iterations of these devices, but the fact is that we still were facing with two fundamental challenges. The first challenge was no matter how good the device engineering can go, the single microfluidic devices can process only about a certain volume. Maybe a microliter can be processed. And because of that, the maximum concentration factor we can achieve is about 10,000 or maybe up to 100,000 fold, but nothing more than that. So we started to think about the alternative. Okay, if you cannot engineer the unit concentrator differently, then why don't we simply multiplex them? So instead of having one concentrator that can concentrate 1 billion times, let's just make 1,000 or 10,000 of them in parallel. And each concentrator can concentrate a certain amount, and then we can recollect and reconcentrate it. That was the one breakthrough we came across to address this challenge. The second challenge we are facing is that, okay, typical biofluid we are talking about is really complicated. Not only you have a target biomarker, you also have all these other molecules that you would rather not want to be concentrated. So how do we solve this? We came up with a platform where we can selectively concentrate only the target molecular groups while passing all these other background molecules such as serum proteins and other metabolites. So by combining these two recent innovations, we published this very important paper in my personal opinion, and it was a great milestone for our group. What we defined as a hierarchical high throughput concentrator system. So this device is relatively complicated because its device job is really bridging the volume gap between a milliliter and the picoliter. So it has a multi-stage concentration steps. So in this implementation, we have 4 stages. And what it does is that as you go through each stages, you take a larger volume starting from milliliter and then reduce the sample volume without losing them into smaller and smaller volume until we reach something like a picoliter range. And if you do the number, that is effectively achieving almost a billion-fold concentration. And that would lead to almost a billion-fold signal enhancement. So let's put this device in the context of the other state of the art, which is a PCR. So the PCR chemistry can amplify even a few copies of a molecule in the sample. And it takes about an hour of an amplification chemistry. But after that, you can actually amplify the molecule to the tunes of about billion-fold or more. And one of the problems is that if you just amplify for too long, say 35 or more cycles, then this PCR chemistry can be very noisy, and it ends up amplifying a complete noise signal. In fact, DI water even can be amplified after 35 cycles. So, compare that with our performances. We are achieving almost a billion-fold concentration, as you can see, with about 3 or 4 stages of concentration. So we are really bringing the concentration below a femtomolar to hundreds of micromolar level. And we were able to achieve that within 30 minutes without suffering these issues of non-target amplification. So for example, if you put in the D, you don't see any signal, even if we try to amplify it more than a billion-fold. So this is really matching what we can achieve with. So what does that mean in reality? So we detect clinical level sensitivity, PCR level sensitivity from the raw samples, such as urine or serum, without utilizing any complicated chemistry or incubation. It is really, in this implementation, we are simply using a hybridization. So our target molecule is, in this case, is a TB marker DNA. And then we simply design a PNA probe, which is a complementary nucleotide molecule, and we labeled it. So if we get a sensor, and then we can measure the fluorescent molecule. If we don't have the target, and we don't see anything. So as you can see, we are routinely achieving tens of attomolar sensitivity, even from complex sample back. And if you put these in the context of other amplification-based strategies, PCR or CRISPR, we may be a little bit less in terms of amplification factor, detection limit, but we are much faster, we are much of a lower cost, and we are not sensitive to any other effects, such as molecular background or primer design issue. So we think that our idea is very complementary and also effective. Now, let's put this in the context of current COVID pandemic. So one of the challenging detection that we still cannot do is the detection of the airborne viruses directly from air sampling. So there are a lot of reasons why we should be doing this. Obviously, well aware of, COVID-19 is transmitting mainly through the airborne transmission, but also there is a fundamental detection problem. Why? Because the way we detect the coronavirus right now, even with our nasal swab, so we do our weekly swab, and we typically dunk that into a volume of liquid, typically about 1 milliliter or so. And that typically contains about 10 to 100 copies per microliter. So if you sample that microliter and put in the PCR, then we have that current detection limit, which is about 10 copies for microliter. But for asymptomatic cases, sometimes we lose that copy. Now, if you think about the airborne detection, the airborne samples can be sampled into much larger volume by the technology called liquid impactor. And those virus copies in that volume is much lower, typically about 0.1 or less per microliter. So if you take the microliter of that liquid, there's no way you can detect those viruses. And similar situation can be found in wastewater detection. So no matter what the detection scenario might be, we have a same problem, which is that we have a large volume of initial sample, 1 milliliter to almost a half liter. But our detection chemistry is operating almost always less than a microliter or 10 microliter. So if we can somehow bridge this gap, if you can concentrate this rare target into a smaller volume, such as a microliter, 10 microliter, we can do a much better detection, much more specific detection and surveillance, even detection of unknown samples by sequencing. So we have been working on this idea, which I define as a high throughput or large volume concentrator. So in this system, the mechanical principle is almost the same, but the unique difference is that now we can pass almost a milliliter per minute flow rate. So with this, we can start from almost a half liter volume, concentrated that down to about 100 microliter, with the recovery hovering around about 50% or so. And we can also still achieve a selective concentration. We can only collect the nucleotide or virus bacteria while passing background protein. So using this, now we are demonstrating that we can actually go below the limit that is posed by the sampling limit, which is 10 copies per microliter. And this comes from the fact that most of the PCR reaction cannot be done more than a 10 microliter volume. Now, with this concentration, we can actually bring this further, beyond that limit, which is 0.1 copy per microliter, or even 0.01 copy per microliter. So we think that this is the way forward to really break through the current detection limit. Thank you for listening, and I would like to show the faces of two people in my group who really behind these two unique concentrators. And I would be happy to answer any question you may have. Thank you.